So yeah, to those who just joined, I may have just turned the recording on a couple of minutes in, but I just wanted to start by presenting the agenda, saying that we're going to be building on the meeting from ICIS last year. Start with a short introduction to people who want to say who they are and very quickly what they kind of do, what their interest is in heat flow. I want to present a quick summary of the report of where we were last year with the ICIS group meeting and the heat flow white paper that's come out. Then Pippa was going to hopefully introduce how heat flow is going to fit into the new SCARGHE science programs to whatever level that's so far determined. Anya's asked to present some work on the Lithosphere of East Antarctica Coordinating Committee. And then we've got a few kind of more general areas. I've got some prompts here to try and discuss. So existing regional and continental models, direct and indirect measurements and model validation, and finally, future directions. So we'd start with, so some people have given me some slides. So myself, I'm a geologist at the Antarctic Survey. My work with heat flow started collaborating with the guys at the Jackie and Joe down at IMAS in Hobart, trying to integrate spatial variability with heat production archive, and was involved in the white paper that came out recently. Jackie, if you wanted to say hi.
Yeah, hi everyone. I'm Jackie. I wasn't able to join you in Korea. I was very pregnant at that point, and now I have a screaming baby down the hall, but I'm trying to ignore her at the moment. I am a geologist at UTAS. I know many of you, some of you I may not know. I'm interested in Antarctica for all sorts of reasons, its tectonic evolution, and yeah, more recently, working with some of you to understand the heat flow and particularly the crustal contributions of heat flow. Thanks, Alex.
Thank you. Oh, I should be I'm giving all the treats now. So Anya, if you want to say hi.
Good morning, good afternoon, good evening, everyone. I'm Anya Redding. So my interest in heat flow kind of comes from really wanting to understand the deep solid earth beneath Antarctica. Heat flow is a very sort of intriguing, I won't say observable because it's hard to observe, but it's a very intriguing earth property. So there's lots of people to get through, but I have a pretty diverse interest, and sort of pertinent to this discussion, I'm really interested in kind of information theory and the optimization of field data collection. We've got some deployments recently funded, so a kind of an ongoing program of investigating East Antarctica. And I've got a few different roles, but this group might be interested to know that we recently got a strategic research initiative funded in Hobart, which is pretty exciting, and gives us a little bit of an ability to carry on in both field and computational efforts. Thank you.
And Felipe, I don't know if you want to quickly say hi.
Yeah, sure. Hi all. I'm Felipe Napoleoni. I'm a PhD student at Durham University. I'm working on subglacial hydrology and ice dynamic in the elsewhere subglacial highlands. And I'm interested in the geothermal heat flux as a potential source of ice-based melting and subglacial water production within deep troughs. And I'm looking at some geophysical and petrological approaches for regional estimations on the geothermal heat flux. And what I want to show in this figure, which probably has a lot of information, the key point here is the existence of these or two new subglacial troughs that contains subglacial Lake Sex and subglacial lakes Ellsworth and some other subglacial water bodies. Yep, thanks.
Thank you, Peter. Does anyone want to jump in and say hi?
I can jump in. I'm Derrick Hasterok. I'm nominally a thermal geophysicist, and my interests are largely in continental and global scale variations in temperature of the lithosphere and the thermal properties that go with it, heat production and thermal conductivity. So.
Yeah, maybe also hi from my side. Carina Haeger. My interests are geothermal heat flow measurements around Antarctica, mainly in shallow marine sediments.
Anyone else want to say hi?
Yes, I'm Guillaume Sanchez. I'm structural geology geochronologist working at UTAS with Jackie, and currently working on a global geochemical and geochronological database that is, I guess, one of the input for the heat flow calculation and things like that.
Just go.
Hi, this is Doug Weens. I'm a seismologist at Washington University in St. Louis, USA. And my interests, I guess, are the structure of Antarctica overall from seismology. And, you know, one of the interesting things we can infer from that is an estimate of heat flow. And so I'm working with Shen on his new model of heat flow from seismology.
Hello, everyone. So Stark mentioned my name. It's better than I come to say hi. I'm Shen. I work at the Stony Brook University in New York, which was the center of the COVID. I'm trained as a seismologist, and I'm interested in using seismology to infer the thermal information of any continent, including Antarctica. Recently, I'm working with Doug to further our investigation to the crustal structure to try to figure out the chemical composition of the continent.
We don't have to go through everyone, but if anyone does want to jump in, in a way we actually won't be able to go through everyone because we've quite well attended. If anyone does want to quickly say hi before we move on.
Yeah, I'm Catherine Ritz. I'm from EG in France. I'm an ice sheet modeler, and my interest in geothermal flux is that I think that glaciology can bring some information on the value of geothermal flux by mixing ice sheet, thermomechanics, and observation of either basal water or I work with Giovanni Marcelloni. I think he cannot reach today, but we work because some satellites have measure more or less the first 1,000 meters of temperature of ice. So we think there is some information that can be obtained from that. It is in the context of European Space Agency the project is called 4D Antarctica, in which Fausto is as well.
Thank you very much.
And I am also the Vice President of SCARGHE for Science.
Nice.
Yes, quickly, since Kat mentioned me, first of all, hello to everyone. And secondly, I hope you're all well. That's the most important thing. And thirdly, as Catherine mentioned, we have an exciting new project funded from the European Space Agency for the Antarctica that aims to also bridge the gap a little bit between the subglacial hydrology, the properties of the ice sheet itself, and geothermal heat flux. And we've decided to concentrate for the solid earth part on 5 regions, which is the Amundsen Sea embayment, the Wilkes Subglacial Basin, and Dome Sea region, the recovery in South Pole areas, and Gambertus. And I should say that we're very excited to any community thermal heat flux efforts in the future. Thanks very much.
I'm going to quickly ask, I did say at the start that I would keep the chat open, but I can't see how I share the screen and have the chat. Does anyone happen to know? Just as a bit of housekeeping, no?
You may have to remove the sharing, the image.
Okay. Oh yeah, that is annoying. Okay, sweet, that's cool. I just want to check that I wasn't missing anything. In that case, I'm gonna have to keep jumping between the two.
I think you can do it if you don't have full screen. You can have more windows.
Oh right. Zoom is a little puzzle.
And then you can share one window and still have the screen, have the chat.
Alex, if you go to if you share screen.
Okay. Yep.
And then go to the top, there's a drop down which says view options. Top middle. Yeah, close to there.
Sorry about this. No.
There's something up here? Okay.
I've got this one down here, but that's not it, is it?
We'll let you know if anyone solves it.
Okay, that's fine. Thank you very much. I just thought I should check having opened by saying that as yeah, like I say, I'm sorry if we can't go through everybody, but thanks to those who did interject. I just wanted to, let's say, start by going over what we went over last year, so you know where we were and where we decided to be going from. So we met those of us at ISIS in Korea, so 24 attendees, and this, the report from this is available with the links on the back of the agenda. So we highlighted, so this is a summary of some of the things of the coverage and what's in the report. So we highlighted considerations for seismically derived models. Of these, we were looking at heterogeneities in mantle conditions, uncertainty of the skew of the models, and empirical models, saying that empirical models may compensate for compositional uncertainties. Highlighted considerations for magnetically derived models. Obviously, this is a summary of what was about an hour and a half, 2 hours of discussion. Key points being airborne data supersedes satellite data these days, variable window sizes being a necessity for the Curie depth analyses. Sensitivity tests show more confidence in Curie depth patterns than maybe absolute depths, so absolute depth should be considered. And uncertainty studies would definitely be helpful. We then moved on to sections looking at crustal heat production, looking at how we might be able to implement data for geochemical values of heat production to our models, necessary for improving seismically and magnetically derived GHF measurements, which have implicit use of these values, saying that either gamma ray spectroscopy or bulk rock chemistry can be used for this, highlighting that archive data and samples exist at various institutes. A new compilation at the time was in the works from the UTAS team. And there was a discussion of whether heat production does, as is often portrayed, decrease exponentially with depth. Other considerations that were discussed was the consideration of spatial variability at different scales, the great impact that topography will have on heat flow, and how we may be able to incorporate this into models. And this is definitely an area that I think we need further discussion. Consideration for groundwater effects on heat flow, and shallow ice temperature gradients being able to be derived from microwave emission studies, as Kat and Giovanni Massolini are working on. But say highlighting that with the sensitivity to heat flow temperature, to thermal temperature in the ice sheet is better with longer wavelength emissions. Discussion of validation and temperature gradient derived heat flow estimates. So we're talking about borehole and probe measurements. Be careful of local temperature variation when using these, highlighting that these are very much estimates, not measurements of heat flow. Subglacial lakes being there to provide minimum, sometimes maximum heat flow estimates, but only under the right topographic conditions, where you might be able to accumulate basal water. And further validation can come from conjugate margin heat flows. So that studies like looking at reorganizing Gondwana and looking at the heat flow in the better constrained conduits. And of course, we finished with, we wanted to, as we will try and get out of this, some future directions, trying to work out where we should be going as a group. So these were the kind of aims. Some of these have been done, some are still to be addressed, and it may be sensible to look back at these. So a database of glacial evidence, subglacial lakes and ice drawdown. It said to have a side meeting at SCAR, so I guess that's a tick. A white paper to advise on the new SCAR science programs, so that came out recently, and will be the next section, so you'll, I'm afraid, have to listen to me witter on for a bit. Provide geotiffs of the different heat flow models along with point estimates for Antarctica, a bibliography of selected papers, and there was a discussion about a mailing list for heat flow or whether it should be underneath the SCARGHE umbrella. So I think this is probably worth discussing again as well. So that was that one. Now I'd say I'm going to have to wait on for a little bit longer. So one of the key pieces that came out of this, and Pippa highlighted this and championed the idea, which was the generation of a white paper for SCAR in the light of the reorganization of the SCAR science programs. So we collected 16 authors, 13 institutions, and tried to highlight all of the different angles and methods by which heat flow is researched in geology, geophysics, and glaciology. A background paper trying to expand on this, obviously had to be a very short paper, was published in the Cryosphere, and we tried to target to highlight current challenges and future directions, like I say, to try and advise the new SCAR programs. So these were the breadth of the document. So it's only about 7 pages long, and the last 2 pages are references. So it starts by introducing the heat flow as a concept, the methods by which it's researched, and the aim was very much to recommend future directions. So this is the final section from that white paper, and these were the points that were really highlighted. Doesn't mean these are the only points of research, but this is what came out of this exercise. Key was that heat flow estimates from bedrock drilling are needed to, big challenge we have is we're generating a lot of models, but validation is really a key challenge and the best way to do this. So the RAID program was highlighted. To validate the feasibility from shallow ice boreholes to estimate heat flow without having to drill to basal or close to basal depths. Looking at the microwave emission, but championing the acquisition of longer wavelength data. At the moment, only the shorter wavelength data exists, and this is less sensitive to the deeper temperature profile of the ice. As I said before, considering topographic effects in all models was a key piece that was highlighted. Radar system development for basal temperatures, using basal melt evidence to expand on glaciological estimates, collating available evidence. Improving models of the ice sheet's thermal history was seen as key for any of the to develop the glaciological methods further by which heat flow is estimated through inverse modeling. Expanding the database of heat production, which I know Jackie will be able to provide more information on. Validating models against exposed geology. Developing better 3D models of the Antarctic mantle using samples, including xenoliths and crustal sections. Developing models of lithospheric structure and heat production. Statistical evaluation of models and uncertainties. And clearly communicating any uncertainties in these models. Obviously, a big challenge is how do we accurately get across the uncertainties in what we're publishing. And finally, to continue the support, primarily including through this group, of interdisciplinary communication and data access. So that's a summary of all of that. So lots of little points. Hopefully some of them get their mind ticking over for things to discuss today. And I think it'd be nice if Pippa could tell us all where do we sit within the new SCAR science programs?
Thanks, Alex. The answer is I'm not quite sure, but I can give you a little bit more information. So SCARGHE, which is sort of the umbrella group to this heat flux subgroup, formally comes to an end this year, end of 2020. With the COVID situation, we had plans to spend funds, which we obviously have not been able to spend. They were on funding early career researchers to attend a workshop. We have permission to carry those funds over to next year. So in some way, CERTI will continue to exist to the end of 2021, as I understand it. We won't get any extra funds, but we can spend the funds that we haven't spent this year. So we're thinking about how to sort of repurpose those funds. One of the conferences we were going to support is likely to be carried over next year. So that's something about the sort of the duration that this umbrella group will exist for. The follow-on scientific research programs, the SRPs, I'm not quite up to date. My understanding is they would start in 2021. I don't know if there's an update of that, and Catherine might be able to advise on that. But what Catherine?
Yes, I can answer about this. All the new SRPs will be the reviews are. I'm in charge of the reviews, so they will. It's almost finished, and the procedure now is to send back to the leaders to address all the questions, and when they send their rebuttal of the reviews, it will be sent to the delegates, and we hope it will be possible on a formal point of view that the delegate makes a decision about the SRPs soon.
Do you know when they would start if they are approved?
I would guess 21.
Okay. That's fine. That's enough of an answer for what we need today. That's brilliant. So what I'm going to do is I'm just going to share my screen. Oh, Alex, can you stop sharing your screen?
Oh yeah, sorry.
That's right. Let's see. Here we go. So I think you should be able to see the. Can you see my mouse moving around on a document?
No.
No, wait a minute. I think I slightly, let's try that again. There we go. There we are. Don't share your screen and then move the document. That's a lesson I just learned. This is the document that was submitted to SCARGHE. Catherine just talked about it being in review at the moment. This is actually visible on the SCARGHE website under program planning groups. And if you want, I can send a copy to Alex and he can send it as well.
Great, thank you.
What I've done is I've quickly gone through and just highlighted a few things, the easiest way to navigate around it. This first page gives the overview. It essentially combines several existing SRPs, one of which is concerned with ice solid earth interactions, and then the others are PACE and ANCLIP. They're thinking about past ice sheet and Antarctic climate interactions. They're going to be drawn in together for one large program. But what we are very concerned about is that these sort of detailed questions, the sort of group that we have here today, doesn't get hidden inside a large program. So that's covered in the structure of this. But the big focus, as you can see here, is understanding future sea level change. But the approach is big picture, small picture, modeling, data, processes. So there's a little bit of everything in there. There are three themes, one of which is Earth-ice interaction. So this is where the interests of this group will fall in this new program. I think, with me, there we go. This is a figure which is in the paper which just outlines. So these three themes at the top are ice atmosphere, ice ocean, ice earth, will come together to think about total ice sheet change and sea level change. So you can see that we sit somewhere inside theme 3, but with this sort of overarching interaction between these themes. So the idea is not that we just have CERTI continuing on its own and not talking to anybody else. So there's a desire for a lot of cross discussion there. What we did was then highlighted a number of questions under each theme. Happy for these to be updated and sort of receive input on other questions that you might want to see in here. But this is the section on ice-earth interactions, a couple of paragraphs. And then you can see there, although it's listed as 4 questions, there's several sub-questions in there. And I've highlighted the one where this group, the interest would fall under. So please go and look at this. Look at what we brainstormed around. This was a small group of people brainstorming. There will be other questions, bigger questions and smaller questions. I'm very happy to receive feedback on what you want to see actually happen once the programme starts. With regard to what's actually going to happen, the structure will have 2 chief officers. It's currently being led by Florence Colleoni and Tim Naish, who will stand for a few years, and then new chief officers will take over. There will be theme leaders and deputy theme leaders. So you can see from within there, it'd be good to have a representative with interest in GHF. And then various other sort of contributors to the management of the group. The way it will function, on my next highlighted bit, is that the theme leaders will develop action plans to answer those questions. Those questions are ones that are down on paper at the moment, but they're not fixed in stone. We're very happy to recalibrate some of those questions. And then the other thing highlighted on this page is the programme establishment workshop. So that was why I was wondering when the programme will start. The way this programme will function is we have not decided in advance how it will function. There will be a workshop after the programme starts where we'll essentially work out how we want this whole programme to function. There's obviously question marks about whether that will be in person or online in some way. But my understanding is that we want a lot of community engagement in that, so that we build the structure of how this is going to work. I've highlighted a couple more things. There is a likelihood to be committees under those theme leaders. So the theme we fit in is Ice, Solid, Earth, which would have a lead and a co-lead, but there will be room for action committees under there. And there's room for subcommittees, with an example, as you can see down here, of geothermal heat flow being a subcommittee. So in some way, this group could carry over and exist under the new structure. But it's all to be worked out, so it's not as if we've decided how this is going to work. We've had a lot of input. We're very keen to get input from across different fields, different career stages, people from different countries around the world. And that's something which SCAR has a very, very clear eye on, is ensuring that diversity of the voice that gets heard. So this is for anyone to come and sort of structure the whole programme. I seem to have highlighted one more thing down here. I can't remember what it was. Something which, this is more on a personal note. Through CERSI, we've run several training programs or training summer schools over the last 8 years, which has probably been some of the most fun things that we've done. We've put a significant amount of our funds into that. So this is in the plan for the next program, which is called Instant. I don't know if I mentioned that. Something to do with instabilities and thresholds is the plan for Instant. There's a plan for capacity building and training schools. So if you felt, just looking at the diversity of what we have in this group and the way it crosses over, if you felt like organising a summer school might be a nice way to just build that community and share ideas, that's something that could be facilitated through the programme. I think that's all I had to say, and I'll circulate this document to Alex. Thanks.
Thank you very much. So I'm just trying to scroll down some notes. That's great, thank you very much. Do you mind stopping sharing, or I might be able to just jump over the top of them?
There we go.
If I can find my screen. There we go. Great, thank you very much.
I guess, sorry, Alex, if anyone had any questions, I'm happy to field them.
Oh yeah, did anyone have any questions? That's very sensible. Cool. I'm sure we can fire questions later or via email afterwards.
That's fine.
Yeah, the next section. So Anya was going to update us on this new development, Lithosphere East Antarctica Coordinating Committee.
Thank you, Alex. Do you have a slide or two following?
I do, and you can, I don't know, do you want to wave or just tell me when you want to move on? It's all of your slides in order.
Great, yeah, thank you. Yeah, so at the end of 2019, the International Lithosphere Program, which is quite a long-running European sort of led entity, put out a call for task forces and coordinating committees. And so myself, Kate Selway and Matt King put in a proposal for a coordinating committee for the lithosphere of East Antarctica. And the idea here is to kind of make a bridge from other continents to East Antarctica, intellectually speaking, and make sure that sort of best practice from other continents is sort of being applied in East Antarctica. And I think actually it works both ways, because one nice thing about the Antarctic community is that geologists and geophysicists work together perhaps more closely than for other continents. So it may well be a sort of two-way expertise sharing. Next slide, thank you. So the committee has a small amount of actual dollars, something like 4,000 euros a year over 5 years, and in a very similar way to the CERS initiative. There's very much a focus on supporting early and mid-career researchers. It's interesting in the post-COVID world or the post-2020 world, to think about the best way of doing that. And there will be a meeting sort of similar to this one in a couple of weeks' time to kind of round up ideas about how to best use that coordinating committee. Next slide. So the aims of the coordinating committee really to promote international cooperation on the enigmatic beast that is East Antarctica. Of course, we will draw on expertise from other regions, not least West Antarctica, looking at those sort of key topics: 3D architecture, current plate motions, both horizontally and vertically, heat flow pertinent to this meeting, and sedimentary basins and deposits, and kind of bringing together the field data collection, data compilations, and computer methodology. And then on to the last slide, I think. Yeah, so the very much wanting to complement the activities of SCAR, connecting with the activities of SCAR, rather than interfering or overlapping. We will likely have workshops connected with some of the larger meetings. And as I mentioned before, in a couple of weeks' time, we'll have our sort of inaugural meeting. So I just wanted to flag that to this group because there's a considerable overlap in interest. Thank you, Alex.
Great. Sorry, when's the inaugural meeting?
It's going to be in about 2 weeks' time. I'm just waiting for a reply, probably around the same time as the Apex SCAR meeting. I'm still waiting for a reply from the SCAR folks on that one.
Oh, interested to see how this pans out. Thank you very much. Great. So thank you for the introductions to these sections. I think this kind of brings us to the start of the broader discussion. So I thought it'd be sensible, first of all, just to highlight, as this, if we're going to keep having these regular meetings, it'd be nice to highlight the new continental models that are out. Particularly, so I've got here are slides from the people who are presenting new models at this meeting. And if those who present them just fancy giving a very quick introduction to where this model's come from, and anything we should particularly take note from it. This isn't the opportunity for a full talk, but if you just want to introduce what you've got, that'd be grand. And Bison, I've thought I've plotted yours up here. This is the plot of yours that I've got for used in the white paper, so it compares your empirical model against that of this other Shapiro and Ritzwaller one. I don't know if you wanted to give an introduction.
Okay, a few words here for this map. On the left side, perhaps everybody has been very familiar with this 2004 map of geothermal heat flux. The beautiful part of that old map is that it covers not just the continental Antarctica, but also part of the Southern Ocean. There is a little bit misleading in this plot is that the maximum value of the geothermal heat flux is 100 milliwatts per meter square in the color scale. But if you look at the raw data of the 2004 map, the geothermal heat flux is way beyond the 150 milliwatts per meter square. I think that was one of the troubles it brought to the community, the very high values. Part of the reason is that when that 2004 map was built, it was using the global seismic models to empirically compare with the local structure near Antarctica. So a lot of the structure was used from places like mid-ocean ridge, which has very high geothermal heat flux. And earlier this year, we made a new map, also based on the seismic structure from other places where we have well-measured geothermal heat flux. So in this case, we compare the latest collected lithosphere structure of Antarctica with the North America, particularly the United States. And what we do is we compare the uppermost mantle structure, where we feel that it highly correlates with the surface geothermal heat flux. And then for each place in Antarctica, we try to identify where in the United States it has the most similar uppermost mantle structure. Once we identify those regions, we try to look at the measured local geothermal heat flux in the United States and assign their values to that place in Antarctica. And finally, we build a map like this, shown in the right side. We covered the whole continental Antarctica. In fact, this map is not plotted that complete. I think it was my fault. Our new map actually covers the continental shelf. So part of the Raleigh ice shelf also has our estimates. And you can see that in part of the West Antarctica, the value is much lower. It does not go beyond 150. In fact, our new estimate actually goes only to about 90 milliwatts per meter square, which is much more perhaps reasonable in a continental environment. Another nice thing about this new map is that we also publish the uncertainty measurements. Alex, is it okay for me to share also my screen for the moment?
As long as you're, no chance for a full talk here, but if you just want to quickly show what you've got.
Okay, let me see. So Okay, so this is the map that has been published in the 2020 paper. So on the left side is exactly what Alex plotted, but with a different color scale. But the beautiful part of this map is that we also try to estimate the uncertainties from the structural comparison. So on average, we find that the uncertainty is about 10 milliwatts per meter square for the map we recently compiled. And these uncertainties include the potential bias from the unknown crustal heat generation, maybe underestimated. I think we have both reviewers of this paper in this meeting as well. So there are certain factors that contribute to the current uncertainty. The unknown crustal heat generation model, the uncertainties within the seismic structure, as well as the potential bias from the, we call it well-known geothermal heat flux of the United States, but still that is still has some errors. But nevertheless, this uncertainty, if you compare with the previous, the 2004 map, this uncertainty has see a huge reduction, more than 60% in reduction of uncertainties. So for the conclusion is that this is a much updated map compared to 2004 seismology derived geothermal heat flux. There are certain features in this map that I also want to draw your attention, except that the East Antarctica being very low, which has been seen in other maps produced by like magnetic field. We also see some small scale patterns like in the southern Trans-Antarctica mountain where the geothermal heat flux is substantially higher than other part of the East Antarctica. We also note that near the South Pole coast, the geothermal heat flux is not that high, although it's part of the West Antarctic. The average value is only about 60 milliwatts per meter square. It is highly correlated with the value estimated at the South Pole Dome, which is also around 60, but substantially lower than the other part of the West Antarctica. And then my final note is that near the Thwaites Glacier, we see an elevated value for the geothermal heat flux, which perhaps can play a pretty important role for the future estimate of the glacial dynamics in this region. The result has been published in GRL, and I don't think it's open access. So if you have a problem downloading the PDF, please contact me and I'm going to send you the PDF file. And the co-authors of the work include Doug Wins, Andrew Lloyd, and Andy Nyblade. And we also really appreciate the two reviewers of the paper who are both here in this meeting. Feel free to make comments, either positive or negative. I already seen that in your letter, so about this work, and we really appreciate that during the manuscript preparation as well.
Well, thank you very much.
Thank you, Alex. Let me stop sharing.
Marie?
Okay.
If you wanted to give a few words just on this, I think I also chucked in you threw a couple of slides my way too. So just an introduction on where your model came from and any key points. We know that this is your talks are elsewhere for people to look at in more depth.
Okay, so I will just shortly present what we've done. So in Q, we've been working on a machine learning model, more precisely a gradient boosting regression model, which tries to link the global available heat flow measurements to geological and geophysical features like tectonics, topography, and crustal thickness, and so on. And on the next slide, you can see the result that we have so far, and also the measurements or the estimates that exist in Antarctica. And you can see that it's, in general, slightly underpredicted in some cases. It's also visible in the graph on the right, on the upper right, where you can see the fit between the predicted and the actual values, and the higher values are slightly below the exact line. And on the lower right, you can see the importances that are selected by the algorithm. So it selects MOHO depth, distance to volcanoes, and ridges as the three most important features that we use. So I guess more details are visible in my presentation in the upcoming conference. And if you have any questions, you can also write me an email. Thank you.
Thank you. One question on this. So a paper which I actually wasn't aware of until we were writing the summary work for the white paper was this multivariate regression study in Greenland by Resvan Barhani.
Yes.
Sorry if I've really screwed that pronunciation up. Do you find very so that again they tried to do what appears to me to be quite a similar study, but in Greenland, did you find you got similar results, particularly in the importance of each feature?
So I think crustal thickness, so MOHO depth, is also a very important in their model, but they use different features than I use, so and more features than I use. So that's what I also wanted to highlight, that I really wanted to look more in detail in the features that I used in the model and how reliable they are, and yeah. But the approach is very similar to the study.
Yeah, interesting to see what their conclusions are in terms of the different driving factors. That's great. Thank you very much. Tobias?
Yeah, hello. So this is our model that is hopefully soon out in a paper, and also the slides with more details about methodology and so on. So this work is mainly building on previous work by Lucas and Burton and others. And what is really sort of encouraging to see is that we see some similarities with Shen's work and with Marine Lossing's work, but using a very different methodology. So we refined the methods used by Lucas and others to allow for optimizing them for the available datasets in Antarctica. So this is a multivariate model as well, but having some additional processing steps to deal with the large uncertainties in Antarctica to hopefully improve the estimates. But yeah, in the slides there are additional metrics of uncertainty and information entropy as well that I'm happy to discuss later. I'm also happy to share the preprint if anyone is interested.
That's great. When did you say you think it's coming out?
Sorry?
You said it's in review at the moment?
It's on its way, put it that way.
Yeah.
Been on its way for quite a while, but it should be out pretty soon now.
That's great. Thank you very much. And finally, oh no, not finally, Carina.
Yeah, hi everybody. What we did was we started off with seismic tomography from Shen and Lebedev in 2013, and we used the minimal physics approach to convert those velocities to temperature, and then subsequently iteratively combined it with the inversion of gravity data. And in that way, we were able to create a self-consistent model of temperature, density, and composition. and that temperature model is now already incorporates influences from composition, is correct for that. And this is what we took as the basis to calculate the heat flux. The problem with our model there was that while it's really good at modeling temperature variations, the absolute temperatures were somewhat biased. And therefore, we used geotherms from well-studied cratons in order to calibrate our model. And from this calibrated model, we were able to extract the thermal LAB and use this as a lower boundary condition to calculate heat flux using the heat conduction equation. We did that mostly in 1D, but we also already had some first tests in 3D. And this is still a work in progress, and we're still working on properly calibrating parameters such as mainly heat production in the crust, upper crustal thickness, and also thermal conductivity. And so far, qualitatively, I think our results are quite interesting, mostly because in West Antarctica, the areas with the highest heat flux very well corresponds to the locations of known subglacial volcanoes, like here in Mary Bird Land or around the Antarctic Peninsula. However, the absolute values are still very low, and I think tweaking the parameters, mostly probably the thermal conductivity, could help us also get further, let's say, closer to previous studies and probably more realistic values than the absolute values we have here. And I think if you have further questions, look at my presentation or ask me via email or in the comment section.
Thank you very much. And finally, the people who I have maps from. Derrick, do you want to introduce your isostatic challenge?
Sure. So this is sort of halfway to our final heat flow model. So this is sort of a midpoint. We're using a thermal isostatic approach. So the idea is that you can remove the compositional components to the elevation and reveal the deeper underlying thermal contributions. So this is sort of a model where we've started with the seismic velocities, and we use seismic velocities to estimate densities of the crust. And then from the densities of the crust, we then compute a buoyancy and then subtract that buoyancy off the observed elevation. We also account for water loading, so either seawater or ice loading in this case in Antarctica. And once we remove that, we get this image here, which is essentially showing the variations in temperature of the integrated temperature variations of the lithosphere. So it's not really a heat flow map, but you can use it to sort of say what's the variations in temperature across Antarctica. And you can see that the map is fairly similar to a lot of the other maps that people are showing with heat flow. The big difference though is that you can hide large variations in heat flow by changing the heat production of the crust pretty substantially. So I think that'll probably come up in some of our later discussions.
That's great, thank you. Yeah, because I remember reading on your work in Australia, it says you did highlight the heat production as one of the challenges there, and the other being compositional anomalies in the mantle as being a big another challenge.
Yes, yeah, the compositional anomalies in the mantle can sort of mess with this, but I don't think that that's as large an issue in Antarctica as it is for Australia. At least it doesn't seem to be. So.
Cool. Thank you very much. Okay. Any others? I thought I've noticed that so something that came out of the white paper studies, obviously the geologists and geophysicists often don't discuss the glaciology models. Is there anything from the glaciological side in particular that should be flagged up?
Yeah, I have some results, but based on artificial intelligence as well, to go over the fact that no model is able to produce exactly what we want, because the evolution models that have the real physics in them, they don't for the prisms, they don't simulate exactly the right thickness. And so I'm trying to use an ice sheet model and to train a deep neural network to reproduce the temperature field, and then we will use it in a Bayesian approach with the data from microwave obtained either, for instance, by SMOS. But it's a work in progress.
Right. Oh, interesting to see how that pans out. So I'm just scribbling some notes. Cool.
The first results are encouraging.
Hey, nice. Very exciting. It's good to hear things coming from a very different technique.
Yeah, Alex, if I could real quick,
yeah.
We've actually got 2 additional models that my group's working on. I've got one that's a Curie depth, a new Curie depth model. So the Curie, it's a global satellite model, but it'll have Antarctica as part of it, and that's currently in review. And then we've got another one that we're working on that's sort of a subglacial lake-based one as well. So.
Busy team. Oh, we get to that one. I think I've skipped one. Where are we? Other new constraints. Oh yeah, sorry. New constraints is the what I had next. I don't have any slides on this one. But as we discussed in the last meeting, a key piece is heat production data. I just wondered if Jackie might want to say something about this.
Yeah, thanks, Alex. I've got a presentation on the SCARGHE website, actually, under session 15, that just shows our latest work, or Guillaume's mainly been driving this. So we've developing Petrochron Antarctica, we're calling it at this point. It's a geochemical database primarily, but it's sort of grown to include geochronology and other petrology information, and it's based on the work that Derrick and Matt Gard have done in a global compilation. We're just trying to sort of, I guess, follow that sort of idea and format, and try and bring in as much Antarctic information as possible to support all sorts of Antarctic research, including calculating heat production, and then obviously feeding into heat flow, but also all sorts of parameters that might be useful for geoscience, soil science, biologists, and so on. So our plan is to have this database, sort of version 1, tidied up and released as a public domain product with an accompanying database paper, hopefully in the next, before the end of the year. So yeah, as I said, there's a presentation online about that if you want more information. Guillaume's probably the one to ask about the structure. Yeah, and hopefully that might be useful to feed into some of these models. It sounds like it's a missing component sometimes, or a component that has a lot of uncertainty in the geophysical models.
That's great. Thank you very much. Well, so now I've got just areas of general discussion. Again, I can see that we are quite likely to go overrun here. So sorry. So I thought as a starting point, similarities and differences. This is something that we discussed last time as well. I didn't know if anyone had any thoughts they wanted to raise in general. So to kind of get it going, here's the compilation that I included in the SCARGHE White Paper, with the 2 magnetically derived models of Antarctica and Martos, the 2 empirical derived seismic models, the Shapiro-Witzwaller one, the Shen one, it's a one that we discussed earlier, and the forward-based seismic model of Anya. And then underneath are the summary statistics, so whether there's any real use for a mean map is debatable, but what it does allow is some distribution comparison. And And what I find more interesting in many ways is the standard deviation of these 5 models. Very much highlights the key area of uncertainty being West Antarctica. As many of us are probably quite well aware, we seem to have a generally good agreement in East Antarctica, maybe not so much in certain areas around the coast, but in West Antarctica, particularly the area mapped as the West Antarctic Rift System, seem to have a large disagreement. And something that, this is the plots on the right are something Ricardo put together. So comparing just the general probability distributions of these models. As we can see, this is rather large agreement in East Antarctica again. The West, oh, I've got a little flag. What does this do? Ah, that's how that looks. Nice, yep. So this is, yeah, so the distribution in East Antarctica, West Antarctica showing a bit more disagreement, but then if we compare them, and whether this is a reasonable comparison as well, maybe is worth a discussion. So some global continental rift systems, where we see actually a much larger range of values, particularly to both ends, to high and low values, than we are seeing currently in our models of West Antarctica, which covers the continental rift of the West Antarctic rift system. So yeah, any thoughts on this? I know that Derrick posed one good point of whether the uncertainties really are that small in East Antarctica.
Yeah, if I could just say one thing with that, I think one of the things that goes into these is a lot of these models are based on sort of deeper geophysical proxies, and or are using crust that is crustal proxies that are not necessarily valid for the Antarctic model, and so they probably underestimate the variations in heat production in East Antarctica. Because if you just assume that East Antarctica is craton-like and you look at variability in cratons, a lot of cratons have low heat production, but you'll find that there are some that have high heat production, and I think you can hide a lot of heat flow variations as a result of that. So
the key there is the assumptions of what we're comparing it to. If that's incorrect, then
that's right. And everybody's sort of working off the same sort of basic set of assumptions there. And because of that, you know, if those assumptions are invalid, then we've radically underestimated the variability.
Duncan Young, I see you want to say something.
Yeah, sorry, I came on late. I managed to get the time zones off by an hour. But
sorry, I think that's partly down to me as well.
And it might have already been touched on, but one striking thing about West Antarctica that Wesley Maziero pointed out in the geology paper a few years ago was it sits really low, even when you rebound it. And I wonder if Derrick has some thoughts on whether that has implications for this whole mystery of West Antarctic heat flow. That isostatically, if you look at that, it's essentially continental crust which is sitting around sea level once you rebound it, which is implies low heat flow from the mantle. But Derrick might have some more insights on that.
Yeah, well, we actually get a fairly high thermal elevation there. So once you account for the variations in crustal density and crustal thickness, that more or less accounts for that, and then you get actually a higher elevation in West Antarctica than East Antarctica. So you can't just rebound for the ice. You have to also account for the variations in crustal thickness and density.
Okay, that's good to know, because there was this paradigm from the 2008 geology paper implying that it was low, but if it can be reconciled with what we understand crustal thickness to be, that's good.
Anyone have any thoughts on this? I'm particularly interested if people have any thoughts about this comparison with the other rift systems. Is that a reasonable thing to be doing with West Antarctica?
I have a comment on that. So I think the main thing to consider is that the West Antarctic rift system is a sort of broad, long-lived region of back arc extension. And it's quite different from the examples that you're showing here, in the sense that the amount of Cenozoic reactivation is sort of debatable, really. So we know in the Ross Sea very well that you have focusing of rifting close to the transantarctic mountains, and we know in Mary Birdland, of course, we have volcanoes, and we also have large displacements of the West Antarctic erosion surface. So we have some handle on on Cenozoic probably deformation, but we don't really know in the interior, how much extension we have. And when you look at larger scale, in terms of the global plate circuit, it's hard to really imagine that you have that much Cenozoic extension. So I think, to me, it always worries me a little bit that there's some sort of equivalency between having a large West Antarctic rift system and having high geothermal heat flux. And that's why I rather like Weizen's new product, because it clearly shows that there are regions of the West Antarctic rift system that have actually only moderately elevated, if that, geothermal heat flux. So I think we need to bring geology back into the equation is basically my comment.
Sorry, jumping myself.
Thank you, Alex. Another comment I want to make is that sometimes it's attempting for us to compare the observable geothermal heat flux of West Antarctica with other selected rift systems. But we also need to keep in mind that if we compare other observables, like easy ones like topography, we may find a lot of difference between the so-called West Antarctica rift system with other rift system. For example, if many times people take basin range as a comparison with West Antarctica rift system, but if you draw the distribution of topography, they will have huge DC shift, even you correct for the rebound. So that might lead us to think, should we really take the whole West Antarctica as a whole to compare with other rift systems, or we should only take a look at a subset of the region, a smaller region in West Antarctica, while the other part of West Antarctica should be compared with other tectonic provinces, for example, Sea of Japan or some other type of features.
Yeah, just to point out one more thing, sort of along the lines of the last two of Wiesen and Fausto, is that there's a lot of GPS receivers now around West Antarctica, and there's been no detected tectonic extension from those. I mean, it's hard to measure a super small amount of extension because of the glacial isostatic adjustment is rather large, but nonetheless, it's clear that there's really no current tectonic extension going on. Whereas in the Great Basin, East African Rift, there's measurable tectonic extension going on currently. So then the question becomes, well, how long has it been since there's been tectonic extension in West Antarctica? And that, I think, we still don't really know very well. I mean, there's some kinematic evidence from Grinnell and so forth, but exactly the whole history is not well worked out.
But it's the timing and the nature of it that we need to get a handle on.
I would like to point out one more uncertainty that we rarely discuss, and that is the sample bias of the reference heat flow measurements that we're using. Like many of those heat flow measurements are actually targeted on geothermal heat exploration or mining activities or other interest in very high heat production. So we should be careful when we review global compilations of heat flow measurements as well, and see how well they and how objective they are in capturing the heat flow variations.
If you're targeting high heat flow, you're going to get high heat flow, right?
Yeah.
So any general ideas on how these differences may be best addressed? Potentially, for instance, with East Antarctica, maybe this uncertainty. Hopefully, Catherine's and Giovanni's work might be able to give some better insights on reasonable values through the glaciological modelling.
I must say that I don't think we will be able to give values where the base is at the melting point, because then it's all additional heat. Or we may be able to give a minimum value, but not more, because the additional heat is transformed in basal melting, and it will be useful for basal hydrology, but maybe not for geothermal flux.
Well, would you say that you just have a heat flow minimum, but in some cases you actually have if you don't have melting, you have a maximum, right? So you have this weird maximum in some places and minimum in others. Is that right?
No. When the base is cold, you have the exact. You can infer the value of the geothermal flux, because then any change in the geothermal flux changes the temperature profile within the ice. While when it is at the melting point, the condition at the base is the melting point, and there is very little interaction between the excess in geothermal flux and the temperature profile. And it is a temperature profile that we expect to be able to use from microwave. But I think the hope may be also, it's a local thing. So in places where the bedrock topography makes the base to be patchy with cold and melting, then there is some hope. But not when it is completely melting.
Okay. Anyone else have any thoughts in this area of comparing the different models and how we might be able to address them before we move on to direct and indirect measurements and model validation, which may bring us back to this point in general anyway?
I think all these models are not bad, honestly. I think they all show, like you said, they show pretty broad agreement. And I think doing an ensemble approach like you've got there is actually a good way to go. I think the biggest uncertainty really comes in from the crustal side, knowing what the variations in physical properties are of the crust. So really, I think that's probably the next place that attention needs to be focused, is developing reasonable models of crustal parameters, thermal conductivity, and heat production, for instance.
I agree with Derrick. I think that's a very important direction, and so far it perhaps serves as one of the major uncertainties in our map, and we will enjoy a lot of progress on that direction if new information can be collected.
Yeah. One other thing that might help too is any model that we use to train our various methods on Antarctica, we ought to train those methods on other continents and make sure that they work on other continents first. And I think that's something that a lot of these models don't do, is test their methods on Australia or South America or Africa, or places that have similar crust as well. So I think that's something that needs to be done. Just to that will also increase the confidence in our ability to do these sorts of these models. So
yeah, definitely. Yeah, if we have challenge validating them here, pick somewhere we've got better options for validation, test them, and come back. So one other point I've got down here before we move to the next piece was integration of different data sets. And it's interesting to see the different machine learning approaches that were presented here, where different data sets may be taken into account. And are there different, should we be integrating different methods, different resolutions in different parts of Antarctica? And something I did highlight, and this is largely because of the uncertainty, the largest difference between the models in East Antarctica, unless, as Derrick says, we're off because of the heat production. Being around the coast, is it sensible and how best to integrate conjugate margin data? Does anyone have thoughts about bringing data sets and bringing different models together that we should be addressing? And this includes the more regional glaciological models. So there's lots of studies. So it's obviously here we presented continental models. These are all from geophysics. There's plenty of glaciological models out there, but they tend to be more regional. Is there a sensible way that we may be able to integrate them together? Any thoughts?
Can I make a comment? So of course, independently from whether it helps or not, let's say in constraining your continental geothermal heat flux, of course, there's massive amounts of interest in understanding geothermal heat flux on the continental margins and differences in geothermal heat flux. And there's quite a lot of effort from other communities to compile all of the seismic data and you know, interpretations along the continental margins of Antarctica. So I don't think we have someone that fully represents that perhaps in this group, but it is something that if you were thinking of expanding, let's say, this group might well be of significant interest, because there you do have a lot of seismic data and you do have a fair amount of constraints. Whether that's going to help you onshore, I'm not 100% sure, but it is an area that could be very interesting.
Yeah, it's an area we have a lot more data.
Yes.
I was wondering about the links between this group and the action group Antarchitecture, that is aimed at compiling and retrieving all the internal layers, the radar internal layers within the ice, because these layers can give information on the basal melting, for instance. And I was wondering whether you are planning to have some common activities with them.
That sounds very sensible. That's a good way of looking for heat flow anomalies. So I'm just
this is Duncan again. Yeah, I'm part of an architecture steering committee meeting, and that is it's clearly something that is moving along. The big issue, and that's what Antarchitecture was designed to do, is integrating all these different radar systems, which will have different response functions to things like looking for layer extinction, like the work that Joe McGregor and Winnie Chu have been doing, as well as looking for downdraw, which then the modeling component becomes really critical when you're getting at the determining heat flow from that.
On the glaciological side, are we in a position, or is there a good way of investigating this, now that we have these different models, the sensitivity analysis of these different models at a continental scale? What would be needed to do that? On the ice sheet, the sensitivity of the ice sheet dynamics to the different heat flow. Any thoughts on that? I'm not sure Catherine?
Sorry, I missed your...
Okay, sorry, I was just saying, as our resident glaciologist, what position we might be in to do some sensitivity analysis of these different models. We're seeing we have variation or similarities in different areas.
Oh yeah, I think it would be very useful for ice sheet modelers to have a series of geothermal flux, because we tend to do more and more ensemble simulations And even in the work I am doing to train a neural network, I use 2 maps, and then I add 2 other maps where I just add noise to the first 2 maps. And so I think having a diversity of geothermal flux of maps, it's very useful, and also it gives you the sensitivity of the ice sheet model and everything that is related to the evolution of the ice sheet, how dependent it is on the geothermal flux in ensemble approach. And this is really, so that's why having the T from Antarctica could be a very useful product for ice sheet modelers and the uncertainty.
Yeah. And one final point I have scribbled down here, because we did brush upon it last time, is topography. I mean, what's the state at the moment of considering, is topography included in any of these models so far? Has anyone put thoughts to this? I mean, this is definitely an area.
Yeah, I can say something about the status of the topography.
Sweet.
That paper should come probably soon. It has been reviewed twice, but it's now with the editor now for very long. So, you know, could be time. We cannot change that, but hopefully it comes soon. But that is in its way.
Okay.
For Antarctica and for Greenland.
So what does this show? This is the sensitivity to topography, or is topography integrated into a different model?
This is the effect of topography on geothermal heat flux.
Oh, nice.
Yeah. So it takes the Martos et al. 2017 and 18, and then the topographic effect is computed and then included into this generic or background geothermal heat flux for the continent.
All right. Oh, that'd be fascinating. And what topography model do you use?
What?
And what topography model were you using for this?
It's a bed machine.
All right. So yeah, that'd be really interesting. Where's that going into? Sorry, just so I can keep an eye out.
The journal?
Yeah.
Is JGR. Earth surface.
Yeah. So hopefully that'll come out soon. That'll be sweet.
Hopefully the editor opens the the web application. Yep. Okay.
Do you have any suggestions on that note for how other people may best integrate topography into models? Anything we should be considering?
Well, what we show is the technique on how to do that.
Yep.
How much it changes the background values. It can change it even 200%.
Oh, right.
Yeah, it can change a lot. So if you are studying a specific ice stream, it's important that the ice modelers consider the effect of topography into the geothermal heat flux. So we are providing 2 maps for continent-wide that are already includes that topographic effect. But taking as background field the Martos 2017 and 18.
Yasmina, what model are you using to estimate the heat flow from topography?
Wow, it's not like a model itself that you compute. It's more if you think somehow of the topographic effect on gravity. Okay, so when you calculate the topographic effect in a specific spot, or the gravity effect of topography in a specific spot, you do these kind of circles that they go from inner circles to outer circles and compute what is the gravity effect of each spot depending on the radius.
Okay, so you're doing, all right, I see what you're doing.
That's kind of analogy. That's how I best can explain it.
Yeah, well, there's another effect that comes in with topography, and that's it's not really topography so much as a thermal refraction effect. So the variations in subglacial topography actually perturb the thermal field near the surface, and you can get fairly large, sort of 20 to 30 to 40% variations in heat flow as a result of variations in topography. Now, I know there was a paper a number of years ago by Van der Veen et al. That had sort of looked at that, and they're using entirely the wrong physical model. So we now have a paper in review in Journal of Glaciology looking at that, that's actually using just computing the heat flow equation and looking at how variations in subglacial topography affect estimates of heat flow, and also how you can get variations in heat flow from thermal conductivity variations in the subsurface, shallow subsurface. So things like geologic contacts can actually have they actually have a larger influence on sort of small wavelength variations in heat flow. So you can sort of have a 50% increase in your heat flow just as a result of two different rocks of two different compositions in contact with each other beneath the ice. So that's a small scale variation, but that could be significant if you're looking at glaciers.
I think that's very interesting, and I think we discussed this in AU, last AU. You showed that to me, and maybe it would be interesting to combine that with the effect of with the other effect that I was talking about.
Yeah, I fully agree on the last point, that the topography can have an effect even at the interface with ice. We had evidence in the Little Dome Sea area of that, and it's an effect of concentrating the heat flux due to the topography. And we have to be very careful from the glaciological point that when you see a lake, sometimes this effect may indicate a hydrothermal flux, and while it is only because there is a kind of a valley or bowl and a concentrating effect. So it's a rather important question when dealing with a inversion of position of lakes.
Alex, can I make a comment as well? So Derrick was mentioning before the East Antarctica, and of course the variability that we do know that they are in certain cratonic regions, and of course East Antarctica is a collage of different provinces. But one thing that's absolutely remarkable of East Antarctica compared to many other cratonic, in inverted comma, regions is indeed the topography. So you have the Wilkes Subglacial Basin with basins going down to 2.1 kilometers below sea level. You have the Denman Glacier with elevations reaching 3 kilometers below sea level. You've got mountain ranges like the Alps, in the middle of the so-called Craton in the Gamburtzes. You've got elevated topography. You've got narrow valleys. So it's really quite an interesting thing, I think, to look at the effect of the topography and the geology at this smaller scale. And perhaps it's really a somewhat unique natural laboratory to look at this, because there is so much topography in this, generally speaking, lithospherically at least, cratonic region. So I think that's really quite an interesting thing. But there's another thing that's interesting, is that this topography has evolved over time. So we have, done studies with my former PhD student, Guy Paxman, showing that there has been a lot of erosion, a lot of flexure, a lot of change in this topography through time. So when we look at ice sheet models that inform, the future, and we look at the past to inform the future, it's also important to consider that the topography and the geothermal heat flux will have changed through time. So those are I think a really interesting sort of medium to long term questions that might also link the activities of this group to the paleo ice sheet community.
Thank you very much. So yeah, sorry, I didn't realise we are now at the hour and a half, so we are running over time. I hope that's not a problem for anyone. I'll try and move along. The next section, before we move to future directions and wrapping up, was direct and indirect measurements and model validation. So boreholes and probes, and how best to validate the models, which so we've already kind of brushed on to some extent. Is anyone aware of any new data that's being released or coming that we should know about? Nope. Have there been any developments in model validation, and how best should we be presenting uncertainties in local and regional estimates and models? Is there a best practice that we should be considering? It was good to see, Jason, you present uncertainties on your empirical seismic model. Any thoughts on these? Okay. I say these are points to just to get discussion going. If there's anything that I'm not covering, always feel free to jump in. Next 2 points I've got scribbled down, and like I say, these are just thoughts.
Alex, can I just jump in real quick?
Yeah, go
so
ahead.
We have been looking at the, because we've been looking at new Curie depth models, we've been trying to figure out what's causing the variations in heat flow estimates from the different Curie depth models. Yeah. And we found, at least for the satellite-based ones, they require a sort of a long wavelength Curie depth estimate to start with, because you don't have the longest wavelengths, because that mixes with the core field, and so you have to sort of come up with your own model that you stick in there, and that actually has a huge impact on the result. Okay. So it's kind of like you're already biasing your model with whatever long wavelength model you're putting in. So I think some of the Curie depth models you have to be a little bit careful with. I don't know if Martos's, if Yasmina's method has the same issues or not, but I know the satellite ones certainly do. So I think we have to be a little bit careful with the satellite models.
Well, I can add something after your comment. Is that, well, we use mostly airborne data to do the spectral analysis to derive the Curie depth or the bottom of the magnetic sources. And we have now applied the same technique to satellite data, and we obtain the same results, or very similar results, let's say. So what it's telling us is that we can use the satellite magnetic to apply the spectral analysis. Of course, the window sizes, wavelength, and so on, they are different, but we can obtain similar results.
And are you using sort of a single susceptibility, or do you have variable susceptibility in your models?
I think you refer to you're using dipoles?
Yes, that's right.
Yeah, no, we don't use dipoles, so we don't need any susceptibility value. Okay. In your case, are you making variation of the thickness and also the susceptibility?
No, there's too many free parameters if you do that. So you have to just leave it to one variation.
So which one are you?
We're varying the depth.
Okay.
Yeah.
Thank you.
I think a very important comment is that when you look at the depth to the bottom of magnetic sources, you're not necessarily looking at Curie depth. I think this is important to consider, because, for example, as Jörg Ebbing, for example, showed, when you look at continental margins, where, let's say, you have a lot of seismic data and you can, constrain the structure quite well, and you've got quite good thermal models, also because you can look at the subsidence of your basin, so you can look at the evolution of what's actually plausible and the amount of extension and all of that. You can see that very often, you know, you get considerably shallower depth to bottom of magnetic sources. And the reason for this is quite simple. For example, you can have regions that have been affected by orogenic events prior to rifting, and they feature anomalous, for example, lower crust, which may not be that magnetic. And I think that's a very important thing to consider when you look at West Antarctica. We know that West Antarctica was a site, you know, of long-lived subduction. You could expect, in fact, you've got exposures of anomalous lower crust in Murray Birdland. So there's no reason why this cannot be the case in West Antarctica. So I think it's very important to construct geologically, say, informed models to interpret what you see, the depth to the bottom of magnetic sources in thermal terms as well. And that's where geologists could also help you in the exercise, because they know a lot about the lower crust as well.
Okay. So I think I'm going to close the broader discussion there and move on to the final point, which is future directions for heat flow research and this group. Are there any planned activities that people would like to highlight? And something I think is important to discuss is should we as a group be looking at a deliverable product, and how specific could such a product be in light of the evolution of this group? Does anyone have any thoughts on this, or any activities that haven't been highlighted so far that they would like to highlight?
I think it would be good to develop sort of a combined approach where we all sort of use our various expertise to come up with a single holistic model, one that sort of incorporates sort of each of these elements, whether it be the seismic or the thermal or the thermal isostasy or Curie depth, and can incorporate all of those into sort of a single code that sort of tries to fit all of those parameters, or gravity as well, tries to fit all of those parameters simultaneously. There's sort of a modeling software that a lot of lithospheric people use called LitMod. Sort of Juan Carlos Afonso is sort of the author of that code. And it allows you to sort of stick everything in the kitchen sink in, and it does a pretty good job of dealing with petrologic models in the lithosphere as well. And I think maybe an approach that did something like that might be a good way to go, so that we're all using our sort of areas of strength and coming up with a single coherent model. One that matches, like I said, will match a lot of observables at once rather than just single observables like a lot of us are focused on.
I'm guessing that approach gives you some level of uncertainty, spatial uncertainty as well.
Well, I mean, in order to do that, you sort of have to do you have to put your uncertainties and the parameters that you have in and just sort of compute it a whole bunch of times and see what uncertainties pop out, I think. But
yeah, probably good.
It is at least a method to see places where you cannot reconcile the various data.
Yeah, that's a good point.
If I can jump in. Hi, it's Jörg from Kiel. We did a LitMod modeling for Antarctica. So I guess, and I agree that's a good software and with the development, but we're still biased at the what kind of data we're using in terms of seismic tomography and so on. So it's really depending on the input data. So I think it's really, and I agree with Derrick, we have to make a consistent approach and bring all the expertise, but also the database has to be well established, because that's a major problem. Also what Marijn found out, like machine learning works nice, but the data sets we use are crap for Antarctica. They're really good for Australia, South Africa. So that limits how much you can actually link it. This is also the main problem with the Greenland study, that they use global data sets, which the crust and thickness were completely wrong for Greenland. So it's a good method, but if you use not good data, then you're limited. And I think this is why we need more pathological data and so on to really, especially for LitMod, which is based on some mental pathology, and we need some information like Adam Martin has and so on. I need this database, which he was planning to establish.
That was a database of mantle samples and xenoliths, wasn't it? It was building into the Joel London publication.
Yes.
Any other thoughts in these areas?
I guess my other comment is on the scales. So I guess you have two sort of fundamental issues. One is attempting to reconcile at continental scale, or even better, as Derrick was saying, combine different methodologies to produce a more coherent continental scale view of geothermal heat flux. But you also have a second challenge, which is perhaps a slightly longer term challenge, which is to produce more detailed models of geothermal heat flux at catchment scale. By catchment scale, I mean glacial catchment scale, because of course then you could look at the impact of such heterogeneity on individual systems. And so there are two sort of challenges. And of course, to an extent, they're interchangeable, because if you develop good approaches to integrate different data sets, then you might be able to also push the boundaries also at sort of regional scale, and also plan, testing in certain areas, new field activities, drilling, and so forth. So I think you have to think in terms of two sort of different timescales, perhaps, of challenges. I think that might really help, develop some sort of plan of work for the group as well.
I think that might work well with something that's as clear as we, there's a lot of work that's done in heat flow studies involving glaciologists as well as geologists and geophysicists, but they are not as well represented in this meeting or previous ones. But this regional scale is the kind of thing that would fit very well with the studies that they've already done. So most of the glaciology models have not been done on a continent scale, they've been done on a regional scale. But that may work very nicely if you can try and, as a way of fitting these two together and working on a catchment scale rather than the continent.
I can make a comment about sort of, where this fits in the SCAR structure.
Okay.
Okay, Alex?
Yeah, sorry, I just had to turn the speakers up.
Okay, that's cool. The two things struck me. Firstly, we're tipping towards conversations about almost quite a significant piece of community work here. My understanding is that there are, I'm not even sure if I'm going to get the term right, SCARGHE groups, of which Antarctica is one, that can exist in their own right for a limited period with the goal of an actual deliverable. So something that could be considered as CERSI comes to an end is whether you wanted to become a group, if you were thinking of putting together. And someone like Duncan, who's on here, or maybe Rob Bingham, would be able to give insight into how that works and sort of how much input there is to a community activity like that. The second point to make is that this is an awesome discussion, and all ice sheet modelers should listen to it. And so what you might have noticed about this year's SCAR conference, which is sort of happening, was there were fewer sessions and they were quite broad, and that was a conscious decision from the steering committee to get people from different groups in the same room. And I think that is also a desire of the new SRP, the Instant Programme. There's an appreciation that groups will need a space to have these discussions, but also an acknowledgement that actually having other people listening to these discussions is really beneficial. So that's something that will happen. So there was just 2 points to make about how SCAR can sort of facilitate some of this work.
Yes, the new arrangement may help solve that problem.
Yeah, there's almost two routes you might want to consider, and maybe go along both of them.
Yeah. So trying to take, while staying coherent in our area of study, also try and take the opportunity to broaden our interest, and especially given that we are obviously trying to target one of the areas, obviously not the only area, being ice sheet sensitivity to the heat flow. Any more thoughts before we close up? No? Okay, well, thank you, everyone. Hopefully that was helpful. And yeah, that was great. Cheers.
Thank you for organizing.
Thank you very much.
Thank you, Alex.
For joining me in your different parts of the world.
Thank you.
Thank you.
Thanks.
Alex.
Thank you. Bye.
Bye.